Hello, this will be section 7.8. Seven point eight is the regiochemical and stereochemical outcomes for E2 reactions. We will learn what regiochemical and stereochemical mean. We've talked about it a little bit already, but we'll have a small refresher. And we'll talk about specifically what makes E2 reactions special and useful for synthetic organic chemistry. Now, think about this reaction. You have an alkyl bromide that has 3 beta carbons attached to the alpha carbon. And on one of the beta carbons is a gamma carbon. The thing about E2 is that sometimes you can get more than one product from either the external alkene, where the alkene is is on one of the outside carbons, or the internal alkene, where the double bond is with the internal carbons. When you do this reaction in a lab, what you find is that there's a preference for one over the other, and it depends on the type of base you're using. And before we go on, I should say that the internal product is called the Zaitsev product, and the external product is called the Hoffman product. Both of these are named for the person who invented them or who discovered them. Oh, Hoffman's name actually has 2 N's on it. I should fix that real quickly. We don't want Hoffman to get mad at us. There we go. These 2 products can be selected just depending on which type of base you use. If you use a small base that is capable of picking out really either of the protons, either one on the this side over here or on this side, you can have a mixture, 70% Zaitsev product, 29% Hoffman product. But as you increase the steric bulk of the base, here, this tert butanol, or this tert butoxide, this base is much less able to get into this proton here, the one here on this beta carbon. And because it's much less able to deprotonate the proton at this position, you don't have as much of the Zaitsev product. And so the Hoffman product now becomes the major product formed. If you increase the steric bulk even further, you see that the major product really shifts to the Hoffman because this very large base now really can't get in and deprotonate protons from this carbon. So the Hoffman product predominates and is the vast majority product there. So just as a quick reminder, the Hoffman product results from deprotonation of this proton. Oops, I should draw it like this. There we go. That proton, and the Zaitsev product is from deprotonation of this proton. Oh yeah, before we go on, I should note that this is called regioselectivity because there are 2 different regions of the molecule that can have the overall reaction occur to it, or the product functional group occurs in a certain region over another. And it's called regioselective because you're selecting for one region over another, and that can change based on the type of base you choose. There's another type of selectivity we can have called stereoselectivity. And this selectivity occurs by making different stereoisomers of a compound depending on depending on the reaction conditions you're using. For instance, take this alkyl bromide. This alkyl bromide has 2 beta carbons attached to the alpha carbon, and upon deprotonation with sodium ethoxide, as you see here, you can get either the trans or the cis alkene. Both of these are stereoisomers, So the fact that you can select for one stereoisomer over the other means that this is a stereoselective reaction. And the question is, why does this happen? Why do you have selectivity of one isomer over the other? And in short, because there are two available protons for deprotonation, and we know from our past lectures that the trans alkene here is more stable. We know the trans alkene there is more stable. We can say with relative certainty that the trans product should be in lower energy than the cis product. And because we're selecting for one isomer over the other, we can say that probably one has a lower activation energy than the other as well. And because we're selecting, again, for one stereoisomer, we call this stereoselective. But there's another type of stereochemical selection that we can have in these reactions, and it is called stereospecificity. And stereospecificity arrives whenever you have substrates that only have one proton that you can deprotonate and make the reaction happen. So what do I mean by that? I mean, let's take, for instance, this molecule. Here, you have only one beta proton that can be deprotonated to make the alkene in an E2 fashion based on this alkyl halide here. Notice that the tert-butyl group here cannot be deprotonated because it does not have any hydrogens. These are all CH3 groups. So whenever you run this reaction with sodium ethoxide, you end up getting only the trans isomer. This is trans because you have the ethyl group of higher priority on one side and the tert-butyl group of higher priority on the other. And this is the only product that's observed. The cis product is not observed. And so the question here, really that's being begged to be asked, is why does this happen? Why? And the answer is because pi orbitals, when you make them, must be planar. Remember from our chapter 1 and 2 discussions, when you make a double bond, you have to have overlap between both p orbitals. If you have a situation where one p orbital is orthogonal to the other, then there's no overlap, and that's not a double bond. So there are two possibilities for this reaction to happen in order for these two things to be planar. The first possibility is that the hydrogen is in this position and the bromine in this one. Or if they're going to be planar to make a pi orbital, they could be here in the blue configuration where the hydrogen and bromine are on the same side of the two carbons there. And in order to determine whether one would be energetically favorable over the other, we're going to turn to our old friend, the Newman projection. And the Newman projection is very key in this instance to let us know what the most stable conformation might be, because hopefully you can spot very quickly that the one with red coloring has an anti-configuration, and the one in the blue coloring has an eclipsed configuration. And because eclipsed is so much higher in energy than the anti, we can say for sure that this reaction is stereospecific in that the anti-conformation will always be preferred. So if you have one proton and one alkyl halide, you can only have elimination in an E2 fashion if you have an anti-periplanar or anti-planar type of configuration. And I'm just going to outline this in blue so you can see it better. You have to have an anti-planar configuration in order to have E2 elimination. And because you have to have this, and you only get one product from the reaction, we call that stereospecificity. So that's how these reactions happen for regular alkane, or regular alkyl halides. But what we haven't covered is how this affects the E2 reactions that occur with cyclohexanes. Because remember, in cyclohexanes, you can have a ring structure with a chair, and depending on how the energetics go with the chair, you can either have equatorial, which is generally favored in ring structure or in chair structures, or you can have axial configuration of the functional group. And if you remember from our Newman projections, as you can see here, we're going to look down this plane and down this plane, where this carbon in black is the one down here, and this carbon here is the one coming up here. We can see that if you have the more favored equatorial position of the chair flip, you actually cannot do the elimination because there is nothing planar to that. There's no hydrogen present that you can eliminate. However, when you're in the less stable ring conformation, where the chlorine is axial, you do have the required planar configuration. And because the required planar configuration is there, we know that in cyclohexane E2 reactions, the leaving group must be axial to the proton. So the leaving group must be in the axial position in order to have the planar configuration that we require for the E2 reaction to occur. And this was section 7.8.